Okay.
Yes, so good morning. This is going to be about joint work with one song, postdoc in Vienna, and the questions I want to raise have to do with the Einstein equation, possibly the cosmological constant, and the questions are: can you extend vacuum spacetimes, or can you glue together vacuum spacetimes? So can you realize data on lower dimensional submanifolds by embedding in a vacuum spacetime? Or and what are data on a lower dimensional submanifold anyway, right? So we have two spacetimes. Can you put them together? Or you have a spacetime, an open set, can you extend it? And of course, not just as a spacetime, but satisfying vacuum equation, right? So everything all the questions I'm going to talk about have to do with vacuum equations being satisfied.
But assuming the vacuum equations are using the most interesting example with the Oppenheimer-Snyder model.
Yes, so the question, so I repeat the question for the Zoom people. If I assume vacuum, I'm forgetting a lot of interesting physical examples, yes. And so these methods, you can certainly extend them to other field models, but I'm focusing now on vacuum equations.
Two different solutions. You assume that the lambda is the same or
right, of course. Right, yes, yeah, right. Yeah. Yeah. So lambda is fixed, maybe zero, but maybe not zero, whatever you want. So what's the story and data on lower dimensional manifolds? This is a question which was raised and answered in some sense by our Takis, Timman, and Vernansky recently. So can you find vacuum characteristic initial data interpolating between two sphere data sets? So the issue the following: suppose we have a sphere here with some data, which I'm going to try to make precise. Another sphere here, again with some data. Can you find a characteristic initial data at the surface in so that you get a vacuum initial data? And then this was part of the following construction, that you start with a spacetime, the yellow spacetime here. You have another yellow green spacetime there, and you try to find a bigger spacetime. Everything is vacuum, and you try to find a bigger spacetime where which has a vacuum equation which includes both G1 and G2. And so they give a positive answer to this problem. Kind of, I'm going to explain what it means kind of here. So they tell you the following, that if the data here on this sphere, or actually on this spacetime, are close to a sphere in Minkowski spacetime, and these ones S2 are also closed to a sphere in Minkowski spacetime, then you can do this construction with some constraints. So there are some abstractions, but you can vary some parameters here to do this, and also you can't really connect a given sphere here to another sphere there, but you can connect a sphere on the initial spacetime to a slightly moved sphere in this second spacetime, right? So that was the main theorem. Right. So, I mean, this is only the symptotic region, so everything has to be close to a Minkowski light curve, but I mean, this spacetime G1 could be a black hole, but it doesn't have to. And this time, the main theorem, you just take G2 to be a family of metrics, or Kerr matrix, so it has well, a few parameters, and then you have to adjust the parameters at the green side to make the growing.
You start with initial data, or you have a given
This construction starts. The construction is stated in the paper is actually about connect the key. Okay, the key part of the construction is connecting some data on a sphere here with some data on another sphere here.
I thought one with this paper, and I read this paper, and it is wrong.
Okay.
There are lots of spheres which cannot be connected with the surface.
And so this is exactly
on the Cauchy slide.
This is exactly what I'm saying. That if you have some sphere here, you have to adjust it to do the connection, right? So you have to, you can't move. That's why we put this tilde here, actually, in this picture, right? So if you start with some sphere S2 in Minkowski spacetime, wherever you want, you have so you can do in Minkowski spacetime for obvious reasons. If you have something non-trivial here, because there is a positive mass theorem which tells you that you cannot connect something which has zero mass in the asymptotic region to something which hasn't. So you have to adjust the parameters here.
Yeah, okay.
But then also you have to adjust use, right? So if you just have a sphere Minkowski, which at S1, good. So this is so that's how this sphere data arise. But you can actually have other version of data. So the simplest case would be you take let me just do a general case. You take a submanifold of another manifold. I'm assuming that everything is smooth here, not to have worries about smoothness. And now you choose a number. Well, there's a notion you want to talk about transverse derivatives of geometric on the submanifold. So the right notion to do this is jets. And so essentially, well, roughly speaking, jets are you take an object. I'm interested in jets of a matrix. A jet over the K of the metric will be the collection of derivatives of a metric. Then that's the standard boundary of jets. But I'm going to actually ask a little more. So if I have a submanifold, I'm only looking at jets which come from smooth fields, right? So I'm assuming I have a smooth metric defined in the neighborhood of the submanifold. And then I'm going to call jet over the K this collection of derivatives, which are compatible with some smooth metric defined around this manifold. Okay? And so you can think of this as follows. You give the metric of the full metric, not the induced metric, on this submanifold, and all transverse derivatives as smooth fields on this, right? So that's essentially what it is. And now you can say what a vacuum jet is, because you can just write the Einstein equations. You can write derivatives of Einstein equations on this surface and check if these jets satisfy these derivatives. Right? So that would be, so these are both differential, but also algebraic relations. So I'm going just to show some examples to make this clear. And I'm going to call a jet vacuum if all these equations are satisfied. So that sounds very daunting and not very interesting because you have a lot of these derivatives. Suppose I take K equal infinity, right? So I have an infinite collection of transverse derivatives. And I need to check that all of them satisfy the constraints coming from Einstein equations. First derivative answer. Second, doesn't seem like a very effective objects. And one of the points here would be just to obtain a usable version of these quantities. So a jet will be vacuum if these equations are satisfied, and this is going to be my definition of vacuum data, submanifold data of order K. So this is a collection of all subjects which satisfy this. So you fix a number K, maybe infinity, but maybe 5, maybe 0, and you ask for all metrics which so that the vacuum equations are satisfied. And you can call about space-like or time-like or no jets when now the metric induced on this submanifold has a causal character. So you're still getting the full metric on this submanifold, but the restrictions, so the metric induced on the submanifold is space-like, then we call this jet space-like, and then this will be space-like vacuum submanifold data of order K. So, yeah. So, question.
This is a beautiful abstract definition, but do you have any reasonable way to parameterize this?
Right, exactly. So I'm going to show you simple parameterizations of this notion in some cases. And so one question would be, is there a way of parameterizing it in Arizona? And also another one is, well, suppose you have such submanifold data, can you find a metric which satisfies the equations, which realizes this data? So not only that there exists a metric with the right transverse derivatives, but is there a vacuum metric defined in the neighborhood of the set which satisfies these equations? So a simplest example, take a point, right? Take a point. So then the jets would be just coefficients of a Taylor series of a metric at the point P up to order K, maybe an infinite collection, maybe a finite one. J0 would be just, you give a metric at this point, right? So vacuum becomes just algebraic conditions of Taylor coefficients, and everything is algebraic. We give a sequence of partial derivatives, and they both have to satisfy the, these are just numbers at this point, and then they have to satisfy some equations coming from the Einstein equation. So, of course, if you're free to use whatever coordinates you want for this, I mean, jets are invariant motions, but you, in particular, you can use normal coordinates, and then the first, so the metric is whatever it is. The first derivatives are 0, so you don't have to worry about them. And the second derivatives of the metric can be expressed by the Riemann tensor at this point, and higher derivatives can all be expressed by covariant derivatives of the Riemann tensor, right? So if you just want in the second jet, so the second, so order submanifold data at a point at order 2, well, vacuum, then you just give any metric you want and the right tensor at this point, right? And that would be your data. The right tensor, right? Because the Riemann tensor just, if you want to, so you just get rid of the Ricci part just by hand. And the W alpha beta gamma delta is down. The right tensor is arbitrary at this point. And you make your Taylor series with this, and you get a metric which realizes the data. But this metric doesn't have to be vacuum, right? So it's vacuum to, it satisfies the vacuum equations at this point, but it doesn't satisfy them necessarily nearby, right? So this data psi, P is the submanifold, so this is a point. Number K is 2 in this case, right? And these are all such pairs. And the question is, well, is there a vacuum metric which realizes psi psi1? So psi psi1, the metric and its first derivatives? Yes, every metric will satisfy this because psi psi1 is just saying I'm prescribing first derivative of the metric, so normal coordinate 0. And so every vacuum metric will induce this data. Well, what about psi p2? Well, this is actually not clear, to me at least, not obvious. So if somebody has an obvious way of doing this, I'd be interested, right? So just give yourself a point, a metric. The right answer at this point is there a vacuum metric defined around this point, which has this right answer. It sounds obvious that there should be one, that it's I think, well, I don't know, yeah, well, why not, right?
So this manifold,
can you just take the microphone?
so this manifold is, so this submanifold is for dimension.
One or before? It's a point. It's a point, right? So now the dimension is 0, codimension is 7.
P is okay, so it's of codimension 4. Okay.
Yeah, yeah, or 4 or 2000 if you're into 2000 dimension. Okay, so well, psi p1 is clear. Psi p2 is less clear, and psi p infinity is even less clear, right? And so, in principle, these are just algebraic relations between vacuum equation, algebraic relation between these covariant derivatives. And but can you find a metric which does that? Even in the analytic case, it's not clear. Because so the question is, when can I prescribe, say, the right answer is covariant derivatives, so that the series converges? And so I don't know. Well, the answer is yes. I am going to tell you how to do this for all these questions. So let me remind you that this question is actually quite non-trivial. This is a very similar question arose when you look at stationary spacetimes, and you have this garage multiple moments. So the question is, if I give you a sequence of garage multiple moments at infinity, even a finite one, then you find a spacetime, a stationary spacetime which has these models. And this has been settled by Helmut Friedrich, well, maybe 15 years ago, in a quite very sophisticated paper. The question is how to make sure that the analyticity conditions so this is all right? So if I'm asking you, is there a space-time which realizes the data just in a neighborhood? Of course, one can then, if the answer is yes, we can say, well, can one say something more about it? Good. So this is at the point. Well, there's another example which you know very well. It's can you just take the microphone?
What does it mean, this data, this G mu and this W something? Because you should say that there exists a coordinate system around this point such that this matrix and this tensor has these components, yes?
Yeah, that's the definition of the jet, right? But changing,
the problem is, how can you change G mu and W, changing coordinate system at one point? And this gives you a lot of gauge.
Yes.
So this gauge may, so one should explore that this gauge may kill almost all data. Yes, so G mu must be just 1, 1 minus 1. That's one thing. But what about W? This I am not sure. What can you do with W with coordinate system? So maybe it's not but you take this think about this point data, then of course you can give it a frame, right? So you have your metric,
take an orthonormal frame for this metric and express your W as
And then I
a matrix in this frame.
Construct such a metric in a neighborhood in one section coordinate, then of course you make possible you have infinite range.
Right, yeah, of course. Right, yeah. So I am not saying that the point is the most interesting example, but it is an example because you can just imagine that I'm sitting here and I can measure all the derivatives of the gravitational field at my point. Is there a vacuum metric? Or maybe not, yeah, maybe the Einstein equations are nonsense. There's no vacuum metric with satisfying this. I don't know. But another example is space-like hypersurface space data. So here, I think everyone knows it. So we take an initial data surface. So this is a co-dimension one. You have a Riemannian metric on it. You give a Riemannian metric on it. You give a symmetric tensor for I generate, then you satisfy the scalar constraint equation, you satisfy the vector constraint equation, and then you know that you can solve the Cauchy problem. You get a space-time both to the future and to the past. So just from this data, first, you can find a vacuum space-time around it, and second, from this you can calculate all derivatives already. So you don't need to prescribe the other derivatives. It's good enough to use this one, right? So in other words, if I, in my terminology of size, hypersurface data of order infinity is actually the same as hypersurface data for any order k larger than 2. That's actually the same as hypersurface data of order 2. I need 2 derivatives to make sense of this equation. And it's just this collection of all vacuum initial data. Okay, so that's much ado about nothing, right? So this infinite number comes for free. In the other case, it was the point you needed, obviously, all these things. And then the intermediate cases, like the characteristic initial data, and before I go to that, let me tell you a theorem which I'm very proud of and which is part of the results of this study, is this extension theorem. And the question is the following. So you have space-like initial data now in a manifold with boundary, and can you extend the data beyond the boundary? Okay, so now, of course, here the whole point is the vacuum data, right? So you have this vacuum space-like data, and you want to extend it so that the constraint equations keep being satisfied. And so there are several theorems about it, which I should have listed on the slide. Let's see. So probably Corvino and Schoen would be one of them, where you're taking data which are close to trivial data, and you can extend them to be Minkowski. Similar result by CMAC, close to trivial data, you can extend them to Schwarzschild. There are other extension theorems by Schoen and Mantoulidis. But there isn't a general theorem which says you can always do this, right? And so my claim is that if you have space-like vacuum initial data with boundary, then you can always find a larger initial data set so that the data extend, right? So this construction doesn't necessarily give you something with good properties, but it gives you the existence of always an extension, right? So boundaries for space-like initial data are not a problem. And let me emphasize that it's not. Well, if you know a trivial answer to this, I'd also be interested to hear that. So I will give a sketch of this proof, and this will go through characteristic vacuum hypersurface data of high order, right? So we need now characteristic vacuum data, and you need them to high order. It's not enough to get small order. But so for this, let's crash course on the characteristic Cauchy problem. And you can formulate it quite generally, but there are some nice coordinates which are due to Heisenberg and Moncrief, in which this has a very simple formulation. So, so here I have two more hypersurfaces, U equals 0 and R equals 0, and they're intersecting transversally. And in this case, you can parameterize any metric, whether vacuum or not, in this form which is written here. So these are these Heisenberg-Moncrief coordinates. By the way, this Heisenberg and Moncrief call these normal Gauss coordinates, but Gauss has never heard about these coordinates. So why should they be called Gauss? And I don't know if somebody used them before, but they're certainly very useful. And the first paper where I've seen those is due to Jim Heisenberg and Vince Moncrief. So when you construct these coordinates and you have the two hypersurfaces, you have to decide for one should be U equals 0, one should be R equals 0. So you have to break the symmetry between them. And so
know that this metric can be found outside of this sigma, including those like cones, yeah?
No, I don't, because I only have, for the moment, I don't have space-like data. I only have characteristic data at this stage. So I don't want to.
At the very beginning, you have only initial data here.
No, I don't have initial data here.
You said because you use initial data which you want to extend on sigma Cauchy.
I give an example. Okay. Yeah, I see what you're saying. This will come later. Okay. Okay. Yeah. I will use this later, but for the moment I just want to,
because those surfaces and
this is a construction in space-time. It has now nothing to do with the initial value problem. For the moment.
So this one is extending space-like data, but to do this I need to do some other things. So I'm going to remind you, but is there chalk somewhere? So that.
There is on the right-hand side.
Okay. So for the moment, I only want to assume this, right? I have U equals 0 here, R equals 0.
There is some metric.
No, not at this stage, I'm not assuming anything. I don't want to talk about the characteristic Cauchy problem, okay? Okay, so that's going to be part of the construction. So, so the way you construct these coordinates is that you decide, well, this is U equals 0. You could decide that this one is U equals 0. But we decide this one is U equals 0. Then you take a fine parameter on this. I think that's correct. Maybe I'm wrong about which one you do, but take a fine parameter on the normal geodesics here. So this defines a function R on the initial surface, and then you shoot more surfaces from the level sets of this, right? And so, but you're breaking the symmetry by making your choice U equals 0 here instead of this one, and that's why this metric is not symmetric, even though the problem is symmetric. So, so you see this factor U here. So when U equals 0, this term vanishes and this term vanishes. And so it should, if you are used to no surfaces, it should be clear when this is a no surface then, because there are no dr square terms or dr dxa terms at U equals 0. And the fact that these surfaces are known for all R, there are no du square terms in this metric, no du dxa terms in this metric, okay? So that's a nice parameterization, not only locally, but everywhere. And then the Cauchy problem is very simple. You give beta on the intersection, right? So you give beta here. You give alpha and g on those surfaces, and there is a solution of back-dimensional equations to the future. Right? Now, there's the one catch, there is a constraint, there's this, Relativity, and I think it's an I, right? So I corrected this, that I had an I, I decided it should be a Y, but I think it's a.
R equal constant slice is not.
Right, that's what I, right, that's what I, right, exactly. The message of you are not all no, only the first one, but these ones are all no. And you can make other constructions where you would use other coordinates, but as I said, this one is simple and useful for my purposes. So essentially, the data are very simple, right? So in the space-like Cauchy problems, the data are complicated because you have these constraint equations, which it's difficult to solve. Right here, you have essentially, beta is completely free here, right? There's no constraint on it. And at this point, everything is free. But here, it's not because the Relativity equation mixes alpha and the derivatives of the metric, and this is easy to solve by the conformal method, for example. So what you can do is just you give alpha and a conformal G on this surface, and then this becomes an equation for the conformal factor. So it's really it's easy to find solutions of this equation. Another.
Gauge alpha if you want. What is the alpha?
Let's see, you can probably gauge alpha to be 0. Right. You can gauge alpha to be 0. Okay. In which case you get so this term will drop out, and then you still have the Relativity equation on both surfaces. So if you prefer to gauge it, you can do this. But you can gauge it on one. So that's the catch, right? So I've written this in terms of R, but then you have to, well, in this coordinate system, so there's an equation. I said one, no, 0, 0, right? So 0, and alpha is very simple. It's the choice of the parameters of the, well, we have this no geodesics here, and if they are finely parameterized, then alpha will be 0, right? Alpha is just, if they're not, then alpha will be something else. So when you do this construction, then these two parameters are finely parameterized, but might not be, I'm not sure, maybe you can do both. Well, anyway, so I want to there's a constraint that it's very easy to satisfy. Okay. And again here now, you can also talk about higher order data, but they just follow. And once you have this, you solve the Einstein equation when all transverse derivatives are satisfied. So indeed, you can talk about higher order data on this hypersurfaces meeting at a corner. In fact, it suffices to give them at this order, and you're going to get a solution out of this.
But you would also think about this. Beta is also initial data, but subject to constraint, like in ABM conversion. It's easier to understand this data. Use metric and extrinsic intrinsic curvature plus torsion, and you have subject to constraint, which is a vector constraint.
We'll come to this. I'm going to come to this. So let me say it again, right? So here in this setup, you forget about everything which is to the past of this surface and this surface, right? And you give data here, give data there. You can find the future development here, right? So that's how this feeds into the this picture that I showed, and which I've drawn here. Good. So now the question is, can I find, if I give this data here, can I find a space-time like this? So I didn't know that there are these yellow and green patches. Can I find a space-time like that? So can I find a whole neighborhood of this? Not only a solution to the future, but a whole neighborhood. What about a single branch, right? Can I, if I just give characteristic data on one surface, and that's probably what you were thinking of, then can I find a neighborhood at all? I mean, here I needed the second one to find the space-time. So I give only one, can I find a space-time which goes with it? Now, here needs, for this, both these questions, you need, well, at least for the second question, you need data of order K. And so if you have one single hypersurface and you use the Heisenberg-Moncrief coordinates, and then the fact is that vacuum characteristic initial data of any order can be reduced to something very simple. So you just give the metric and alpha on this, and on a single cross section, I don't need this. Yeah, so you need derivatives of G in this direction. Okay? So you take a single hypersurface, take a single cross section of the surface, and you need G and alpha, so order 0 data, and you need at one transverse section of this horizon, you need, of this null surface, you need to give derivatives of this metric GAP, right? And so rather than giving all transverse derivatives of all the metric fields area, you only give transverse derivatives to the order you want. And that, and the way you prove this is that quantities at one section, you can integrate NOD and get the other quantities. And this is true for all transverse derivatives, right? So for all transverse derivatives can be, of the metric can be determined in terms of this data when you use the Einstein equation in Heisenberg-Moncrief coordinate, right? So this object which looks like a terrible thing, an infinite collection of derivatives of any order, is reduced to transverse derivative in one section, and this feeds up to this Rayleigh equation, right? So you need to solve the Rayleigh equation, and now the point is also that, and that's the main point probably, that these transport equations, so these are equations for these transverse derivatives along the more geodesics of this hypersurface, and of course, and they have unique solutions. So if you prescribe your transverse derivatives here, you're going to get your transverse derivatives at this point uniquely, and it works both ways because it's our first order IDs. So if you start with some data here, you're going to determine them at this point. And if you start with the same data in this point to integrate backwards, you're going to get what you started with, right? So it's a uniqueness in both ways, right? So you can prescribe boundary data here and get the solution here, or boundary data here, get a unique solution there. And that leads me to something which I call the head-trunk construction, czyli metoda Wajchy. So head-trunk is a Wajcha, right? So it's something that you use to start an engine. So it has this shape that you see here. So let's see. So we start with this hypersurface data on this N, right? So this data, at some section, you have transverse derivatives, which you prescribe. At these transverse derivatives, you can find any other data. Okay, so what's the question here, right? Can you embed characteristic data on a surface of order 25 in a space-time? Can you find a vacuum space-time which is a neighborhood of this hypersurface, right? So, and the method is the following: at this section, you know what the transverse derivative of the metric should be. So you put here any complementing characteristic data which have the same Taylor series. And so this is just by Taylor series, you can do this. So when you do this, you can solve the characteristic Cauchy problem to the future, and you get the yellow spacetime. Now, because the transverse derivative of this sphere, you can do the same at this point. Namely, you just take any characteristic surface which has the right Taylor series at the intersection. You solve the Cauchy problem to the past, you get the green spacetime. And now the question is, do they agree and to what order? And that's precisely what is guaranteed by these transport equations, right? That you know that the data, once you've given the data here, you know the derivatives in the transverse direction to infinite order. You've chosen the data at this point to have the right Taylor expansion. So you know the Taylor derivatives to infinite order from the data at the upper part of the crank. And then they agree because you have uniqueness of these transport equations. Right? So therefore, these things will match to infinite order, and with the infinite order of your K was 25, you'll get a space-time which matches to order 25 across this. Good. So once you know how to do this crank construction, let's go back to the extensions here, right? So can you take the microphone?
Listening carefully enough, but I expected you to say that we have some data on this one sphere, some other data on the other sphere, but we have still freedom in setting some data on this N in between. So we use this freedom. So
that's a different problem. That's the problem of joining together to sphere data. But here I'm talking about just the characteristic data. So starting with this, this place, and I'm just telling you, if you have characteristic data on a hypersurface, then you can find a vacuum spacetime around it. And of course, it's not unique, right? So there is no uniqueness because this construction, I've told you, even if you give me an infinite Taylor series here, there is an infinite number of metrics which will match to infinite order. Yeah, well, not metrics, but characteristic initial data. And so, and the same here. Let me mention that this construction actually, you can get some uniqueness, of course, by saying, well, I already know the data here because for some reasons I know them. And if I go all the way to Scry, I know these radiation fields on Scry, and then I get something which is a spacetime which is uniquely defined by characteristic data here and radiation data at Scry. That would be, in this case, you have a nice uniqueness result and description of how many times you can have. But this is purely local, and if you're interested in local problem, that's what you do. And for my extension theorem, so we start with vacuum initial data with boundary, and we want to extend them so that the vacuum equations are satisfied. And we use the crank for this. And that's what probably you like that immediately in mind, right? So these are my initial data on this hypersurface, and they have a boundary here, right? So if you have initial data with boundary, you can solve the Cauchy problem, and you get a space-time with a horizon, and the horizon will be a non-hypersurface which exits from the boundary here. So in a non-hypersurface here, you have smooth initial data on this no boundary. So therefore, you know the derivatives, transverse derivatives of the metric at this point. So you can find any other known characteristic data on this second boundary. But now, so we have a situation where we have a piece of a null boundary. We just use the crank construction to get the green side, and the green side goes a little below. So when you solve the Cauchy problem backwards, you don't go, well, actually by stability, you know that you can find a neighborhood. That this surface sigma can be extended as a space-like hypersurface in the green region, and then you take the induced data there, and that gives you an extension theorem.
Depends on the data on this pattern.
Exactly. Which might be arbitrary, so you have a lot of extensions, which wasn't usable to start with. I mean, you would not be able to have even one. So I'm telling you, yes, you have a lot. And in fact, you can parameterize them by, if you want to, by this hypersurface. And if you go all the way to sky, when lambda is 0, then you can actually make sure that this piece is asymptotically flat. So this is the extending space-like Cauchy data. Well, you can also extend the data on a light cone. And a data on a light cone is a similar to a characteristic hypersurface, except that you don't have two hypersurfaces intersecting, but you start with a tip of a light cone. So since it's a characteristic hypersurface, you also have your characteristic data on the light cone here, and this but you then have regularity conditions of the tip. So this beta, for example, is coming from the tip has to be 0 at the tip if the metric is smooth at the tip. So you don't have some extra information at this bottom here, but you only have data on this on the cone, and you can solve the characteristic boundary problem to the future with on a light cone. And then if you want to find a neighborhood of this point, then you just draw any space-like hypersurface in your solution. Now, by the extension theorem, you can extend it there a bit. And now you can use this red space-like surface as a Cauchy surface to the past. And you solve Einstein equations to the past from this surface. You're going to get a neighborhood of this point and a whole neighborhood of the cone. But in particular, we're going to get a neighborhood of this point if you're interested in. Characteristic data on the cone. So you can solve to the future, and you get this. So let me say it again. You start with characteristic initial data on the cone. You solve the vacuum Einstein equation. You get this, this should have been, I mean, the theorem tells you that there is a small neighborhood of the cone where the metric exists. Right. Right. Right.
So smoothly from initial data on a cone space-time inside the cone. What happens with this?
This is a 50 pages paper which I wrote in 10 years ago. Yeah. Right. Yeah. So the question of singularities here is actually interesting. And it's a bit of work, but yeah. Yeah, there was theorem. Yeah, give characteristic initial data. In a whole neighborhood to the future, right? Now, the picture is this. So the neighborhood is this orange region, which is very small for good reasons, because these existence theorems give you a very small region, right? But it's very small, but you can still draw a space-like surface in it. So you draw this space-like surface and you solve backwards, you're going to get a neighborhood of the point. And now I can answer this question at the beginning. So data of infinite order at a point, right? So data at infinite order at a point. So you want to give data. So the metric and the ordered derivative at a point, compatible with vacuum Einstein equations. Can you find a metric which realizes this? And the answer is yes. This follows immediately from this construction, because you take your point, you take your data which satisfies the vacuum constraint to infinite order. You draw any characteristic initial data compatible with the data here, and this construction gives you a metric in a neighborhood of this point, which solves the vacuum Einstein equations. Okay? So indeed, you can at a point. A metric in this and yellow neighborhood, and it smooths across this boundary. Okay, so this is my favorite. This is a Fledermaus construction. Right? So now, similar question. Now I give you two characteristic hypersurfaces. Can you find the space-time goes to the future and to the past of those, which solves the equations, right? And so, so that's the Fledermaus, right? So you have the initial data on this hypersurface. Where you solve to the future by solving Einstein equations in the standard way. Each of these branches comes with a crank construction, which gives you the right branch gives you the green space-time, the left branch gives you the yellow space-time, and they have to agree to infinite order here, in particular get these little pieces of hypersurfaces where you can solve to the past, and you get this Fledermaus space-time. And that's probably all I wanted to mention.
So all these voltage to the right, to the left, what do you have?
So here you can put any data you want, right? You can put any data you want. And so the space-times are indeed, there's a lot of such space-time that are parameterized by.
To the future, if you have only one space-time, but
in the future, the one you want, right? The difference is data here. Otherwise, but these seven solutions actually parameterized by the characteristic data here.
Mhm.
Good. So the title of my talk was Growing Variations. The G is not accidental. It has to do with the Goldberg variations. So the Goldberg variations are probably the most boring piece of music that you've ever heard. So it was written by Bach, commissioned by a duke who couldn't sleep. So he asked him to write him some music to help him fall asleep. So I'm happy to see another one fell asleep. So we started with Bach and we end with with Strauss with the Fledermaus. Thank you for your attention.
questions? Questions, please.
I can say that this diagram reminds me something not very close to this, namely think about
Can you give him the
now shells instead of matter, distributional matter, and then you can glue through this here as 4 different space times, and there is some nice 4 so there's some stuff in gray, somebody's formula. So the point that you can glue the
can you give him the microphone?
so then the passes are related. They are not big.
So of course you can put shells and everything here. So I mean the point was just to have vacuum because I have to satisfy a lot of equations. As I said, I mean you can modify these constructions to put other things here. Of course, building across an all hypersurface with a shell, that's a standard question. Yeah. Israel and Barbados and so forth, right? So these things are well known. But I don't want shells. I want to have smooth space-times, and that's what this is about.
What about applications?
Well, the only applications I could think of is this extension of initial data, right? So that's an entry goal. I think these constructions are pretty non-trivial, right? But extending space-like initial data is certainly an non-trivial question, or what it is answered by these constructions.
Two black holes.
To construct initial data for black holes, I think there was, of course, these game constructions are used to do things like that, and there was a recent paper by Vashi that constructs initial data with many black holes, or another one by Covino, and I haven't thought about using these constructions to simplify the methods, right? So Vashi and Covino use space-like constraint equation, and that's a very difficult techniques behind this. And these techniques are much more elementary, so presumably you could, I don't know, yeah, that's something to think about.
Are there questions?
I don't know, maybe there are some questions from the internet. Is someone checking that, or I don't see this here.
I have some questions from online listeners.
Well, I don't see any raised hands, so.
Okay, so thank you very much again.